We are still here in our additive manufacturing course. It's me, Rauf Tailony. We're still talking about designing for additive manufacturing. How you can decide the 3D printing method or technology that you're going to use, and how you're going to do a successful design that will be successfully completed with the specific 3D design methodology that you want to follow in terms of 3D printing. We discussed before about the designing for binder jetting. We're still on that topic. Today we will talk about infiltration and sintering. We discussed that binder jetting can be used to produce functional metal parts by doing secondary processes. These secondary processes can involve something similar to infiltration or sintering. The mechanical properties for the full color sandstone parts can be enhanced after printing by using the infiltration, and this can be done by adding a super glue material or adhesive to your printed parts, or even other several additive materials that you can use to modify the properties of the final printed part. Infiltration is usually done after printing, so you put your part in a furnace and the binder will be burnt so that it will leave some voids. After that, the part will be in terms of porosity up to 60% porous. Then we will use a bronze material that can infiltrate the voids through the capillary action. At the end, you will have a part that is having low porosity of almost 10% and a good mechanical strength. You can see here kind of actual process of infiltration. This is an actual part that's being printed using the binder jetting method and being infiltrated as a post-processing technique. For sintering, after you complete your print, then your part will be placed in a high temperature, sometimes in a microwave oven, and the binder will be burnt out and the remaining metal particles will be sintered or bonded together, which will give you a part that is having a very low porosity that is less than 3%. We are talking here about the mechanical properties of the final part because we are designing a metallic part, so we care about the mechanical properties of that part. Usually these parts could be functional parts, and so our goal to reduce the porosity. The lower the porosity, the stronger the material. The higher the porosity, it means there's more holes in the microstructure of the part, which means the part is weaker in general terms. Infiltration and sintering for metal binder jetting usually connected with or accompanied with shrinkage and dimensional reduction. So after doing your infiltration and sintering, expect that your dimensions will shrink and the part overall size will be slightly reduced, and this effect will be more clear in sintering than infiltration, because in sintering there is no new material is added to the part, just the part is being processed by itself, so it will lose a material during post heating and all of the details for the sintering post processing. This shrinkage is usually depending very much on the geometry of the original part that you print. As general rules, the parts that are having a length of 25 up to 75 millimeters will shrink approximately between 0.8% up to 2%. So that's something to keep in mind while designing. Again, if the dimensions are critical for you, then there's no 3D printing that's giving you 100% accuracy of the part. You will always, especially if you are involving post-processing, then you will always lose some of your part dimensions. That's something to keep in mind. For larger parts, it will have an average shrinkage of 3%. Again, these are averaged values. It could differ based on the quality of the material you're using. It's depending on the health or on the accuracy of the printer that you're using. Of course, binder jetting printers are being made by many manufacturers, so results are not all the same and accuracy is not the same. If you are having non-uniform shrinkage, this will be surely an issue. You're not having shrinkage all over the part, but your part will be kind of warped and in an uneven design, and this should be accounted for during the design stage. If you are trying to use the binder jetting technique, if you are doing that with an outsource, then you want to talk with the machine operator. What is the application for your part and what are your expectations to keep in mind? For sintering, the binder jetting parts will usually have internal porosity even after you are adding more material in with infiltration. It will be the parts that you will have will be 90% dense. For sintering, it will be 97% dense in some times. So the mechanical properties will be inferior to the bulk material or the parts that are manufactured with different 3D printing processes. As we mentioned before, the binder jetting can produce a full color prints through jetting the ink and binding the agent on the sandstone or the plaster. So after you do your print, the parts will be coated with a super glue infiltrant, so that will improve the strength of the part and it will enhance the aesthetic part of the colors applied. So sometimes you're adding a second epoxy layer so that you will improve the strength and the color appearance of your final product even further. Full color binder jetting parts are considered brittle parts and they are not recommended for functional parts. If you're going with full color, then usually this part is visual for visual purposes only and not recommended for doing any functions. Usually the color application is done through your CAD software where you designed your parts in two methods. Firstly, either you do a pair face or as a texture map. So it means either you choose each face for your part and you assign a certain color for it, or you are just bringing your own texture or your own image and you are applying it on the part through the software. If you apply the color to the model per face, then this will be easy and quick for you to implement, but it will give you less details of colors and vibrancy for these colors. For the CAD software packages that will allow colors for each face, then the file can be exported using the virtual reality modeling language, which is abbreviated as VRML. If you are using a texture map, then it will be a little bit more complicated and it can be done through an outer software in most cases. Some of the modern 3D design softwares will give you the texture, give you the ability to apply your texture, but it could be tricky. Texture files all most likely are done through GPG, either GPEG or the PNG format, which is a picture format that can be printed on the part face. If all the textures are applied, then the model will be exported as VRML extension or X3D file extension. For post-processing, binder jetting, we said it's a metal-based 3D printing, so there's a limited number of post-processing methods that can be applied. So you can do, after you do your infiltration and sintering, you can do sanding, polishing, or machining so that you'll improve the final appearance and dimensional accuracy of your part. Common metal finishing can be applied as well because they can give you high stiffness and free from any binding during application. Sometimes sand casting cores and molds, they can be used once they are removed from the printer and cleaned from the excess powder. So in this case, we are trying to do sand casting cores or molds that will be used for sand casting molding. So you can be cleaned easily from the excess powder. Sometimes you need to do a kind of thermal post-processing so that you'll improve the strength of these sand casting molds. For full color models, they are dipped or coated with infiltrant material or solvent so that they will improve their mechanical properties. Binder jetting offers full color printing, so in this case painting or dyeing is generally not required. The part can be coated as well in a clear lacquer so that will improve the wear resistance and give prints a smooth surface. So you are just treating a metallic part. You can do all kinds of post-processing done for metallic part as long as these materials will not degrade the original 3D printed part. Just make sure there's compatibility, then you can do any kind of metal coating on it that will serve like a longer life and the better mechanical properties. Applications for binder jetting, you can do a full color prototype. The secondary processes that are used in parallel with binder jetting can allow for production of functional metal parts. There is a large range of metal available, and the ability to create complex shape is possible. In this way, binder jetting can be a good solution for designs that would be expensive and difficult to produce in the traditional ways. So if you can't produce in the market or it's too expensive to be done, then this is the way to go. For sand casting, that's another application that you can do where you can create sand casting patterns and molds because they can give you a low cost and a high speed delivery for the parts, which can be excellent solution to create pattern designs that are difficult or not possible to be produced with the traditional techniques. Functional metal parts, you can create a functional metal parts through this 3D printing process as well. The good sides for the binder jetting or the pros for this technique or technology, that it can produce metal parts with full color prototypes at a small percentage of the original cost compared of the SLM and DMLS technologies and material jetting respectively. The other good side for this kind of technology is that it can manufacture very large parts and complex metal geometries, and it's not limited by any thermal effects as warping. Third benefit is that you can make manufacturing capabilities out of binder jetting because it is excellent for low to medium part production. You can create production parts with a good number of iterations. The bad sides for this method, that it have a lower the parts produced through this technology have a lower mechanical properties than the SLM and DMSL, and that because of the high porosity for the produced parts. And the second thing is it's giving you only rough details, but the parts will be as well very brittle in their green state, and they can be broken during the post-processing techniques. If you compare this method to other 3D printing processes, then it have a limited material selection. You are squeezed with a small spectrum of materials to select from. The process capability, as an overview for binder jetting, the materials you can use metals or ceramics in form of a sand. Dimension accuracy for metals plus or minus 0.2 of a millimeter. For the full color, it's plus or minus 0.3 of a millimeter. For sand, it's plus or minus 0.3 of a millimeter. The build size for metal 400 by 250 by 250 millimeters, up to 800 by 500 by 400 millimeters. For the full color, it's 200 by 250 by 200 millimeters, up to 500 by 380 by 230 millimeters. For the sand, it's 800 by 500 by 400, can go up to 2200 by 1200 by 600 millimeters. Common layer thicknesses for the metal, 50 micrometers. For the full color, 100 micrometers. For the sand, 200 to 400 micrometers. Support is not required in this methodology. The features, if you have a wall thickness, then it should be minimum of 2 millimeters. Unsupported walls should be 3 millimeters in minimum. Embossed or engraved details should be 0.5 millimeters in minimum. Unsupported edges should be 20 millimeters or higher. Fillets should be 1 millimeter in radius. Hole size should be 1.4 millimeter in diameter and up. Scape hole should be 5 millimeters or up. Feature size should be 2 millimeters in length. As a general rules for this kind of technology, binder jetting can give you a good design freedom because you don't need any support structures, and warping is not an issue for this method, but the parts will need to be strong enough to withstand handling in the green state, because they will be weak in green state, so you need extra caution while doing post-processing until you're sure the part is not in the green state anymore. Binder jetting can be used for a lot of different applications, including production of functional metal parts, sand casting molds and cores, and the full color models and figures for visualization. We'll move next for designing for 3D printing enclosures. As I kept mentioning before, we will talk about enclosures in more details for their importance. A lot of the modern world applications need enclosures, especially all projects or applications that are enclosing PCB or a kind of mechanism that is for parts that are usually handheld. Can be bigger than that, but I mean, most likely these enclosure designs become handy for handheld devices or electromechanical systems and so on. So when you're doing 3D printing for enclosures, it will allow you, give you some design freedom, and let the designer print a prototype or final part in a couple of hours. It will be very cheap for him than going to the market, and very fast as well. You don't need to wait for months and years until you get your first part to put your hands on it. Then you realize there's a problem with it, and you redo it and rewait and so on. So it will allow the designer to do a physical inspection of his final design basically in a couple of hours. Now the possible technologies. So based on what you want the enclosure to be used for, what's your application, based on that you decide your printing technology. So if you are trying to do rapid prototyping, trying to do prototyping plastics that are cost effective and quick method of printing enclosures, then the printing technology will be the FDM. For high temperature, high resistance plastics are rated to remain stable up to temperatures as high as 80 degrees Celsius after thermal post-treatment. So in this case you can use material jetting. For high quality surface finish, it's governed by the cost and time, so you can use SLS. Nylon will give you a satin-like matte finish that is grainy to touch, but the material jetting and SLA offer fine detailed models with very smooth surfaces, so you can go with SLA or material jetting for high quality surface finish applications enclosure. For high accuracy, then you go with SLA, SLS or material jetting, because they give an excellent surface finish and does not require any support, while the support used for the material can be, in some of these methods, dissolved and easy to be removed without any dents or marks on the part. If you need your enclosure to be transparent, then SLA or material jetting is the way to go. For flexible materials, then you need to use rubber-like plastic materials, and maybe you can go with SLA flexible resins. Usually these kind of applications can be useful if your enclosure need to allow the user to press some buttons or motion of switches through the sealed case. Now, securing your enclosure assemblies. After you design your enclosure with a certain visual properties, then you want to make sure the enclosure can assemble together. Of course, enclosure means it's not one part, it's two parts that are coming together in a certain mechanical or electromechanical way. So to secure your enclosure, you can go either with snap fits or interlocking joints or threaded fasteners or living hinges. So all of these are possible options for enclosure design and enclosure assembly and connections. If you want to design snap fits and push fits for the enclosure, this does not, if your enclosure is not going to be opened and closed a lot, and there's no kind of wear or fatigue that is expected to the enclosure, then in this case you can go with snap fit or push fit for sure, because it's easier to design and the joint does not have to be and the joint does not have to have a lot of design efforts in order to make it real. If you need just to have a quick prototype, then you bring the upper part and lower part of the enclosure, put them together with adhesive, some kind of resin or glue, then they will go permanently fastened together and will serve the same purpose. We can see here the lips for the snap fit. So this, let's say your upper enclosure may be covered with a plastic part in here or a glass, then it will go, this is the male, will go together with the female part or the lower part of the enclosure. They will clip together and they will keep in place. Then with a little force you can unclip them and so on. Going with screw choice is still a very famous choice. You can see in the market all kinds of enclosures and applications and handheld devices still going with screws, all kinds of and all sizes of screws, because of its kind of plastic to metal property that will keep things in place in a cheap way. This is a living hinge. You can use your enclosure or your box to be able to open and close with a living hinge, and maybe you'll have a snap fit here to keep it in place, to keep it closed. So the main general steps to make a successful enclosure. So first you want to do enclosure planning and components measurements. So you want to be sure firstly that your enclosure size is enough to enclose whatever you want to put inside of it. And so it is useful for the 3D model to 3D model the internal enclosure components along with the enclosure itself, so that it will allow easy clearance checks and help determining the final component positions. So designing your enclosure, then you need to have whatever inside that enclosure. So if we do a little sketch in here, let's go with this. So this is a side view for your upper enclosure. So this is your upper enclosure, right? Let's flip it on his back, like in this direction. So we are looking top view on it. So this is your enclosure now, with, of course, there is a thickness for it. These are the thicknesses for your enclosure, right? So thickness T. Now you want to put stuff in here. That's where your parts will go in here. So you need to know what's the length for your enclosure externally and what's the width. Then you need to know the thickness so you can know what's the internal width which we care about and the internal length that we care about. This is where your components will go. So if you have here kind of printed circuit board in here with a certain dimensions, then if you're trying to keep the circuit in place, then you want to think about the method that this circuit will go in place together with the upper enclosure or lower enclosure. So if you're planning to put screws in here, you want to keep that in mind, because screws need a base to sit on. So this base, side view in here for your enclosure, this base need to be something like this so that the screw will go in here. So you need to have a kind of studs in here to receive the screws. All of them need to be aligned with the screw holes in the PCB, for example in here. So you want to keep that in mind. Let's go back to our slides. So you need to have enclosure planning. You need to look into the internal dimensions and external dimensions for your enclosure and for your internal parts. If you have already a design for your internal parts, then you can assemble them in with your CAD design. If not, then just make a rough estimation and rough measurements for your internal parts and all the related design decisions following. Then you design your structure. You care about tolerance and clearance as recommended, as we will mention, or depending on your printing methodology that you're going with, then follow the tolerances and clearances recommended to be able to assure that you will have a successful print. As we said, depending on the printer technology and calibration. So we'll talk more in details about these bullet points as moving forward. If you have a wall thickness, then the minimum wall thickness for enclosure, regardless of your printing technology that you're using, 2 millimeters as average. That's the recommendation for all enclosure walls. Radii or fillets to the corners. So we have a corner in here. If you want to make a radius in here or a fillet, then these will help. It's important to always do that in all your design applications. Just always make the sharp edges as fillets, because it is a general rule. It reduces the stress concentration at the corner and the edge and make the part easier to be 3D printed in this application or in this case. So small radius can make a big difference and make your parts even it will extend his life before the first crack to show up. For components clearance, you need to allow 0.5 of a millimeter around all internal components to compensate for distortion, shrinkage, and printer tolerances. So this is your internal component, this is your external component. Make sure you have a 0.5 of a millimeter all over in all sides of the enclosure, just to be ready for any kind of deviations from what you planned for. Clearance for holes, you need to allow 0.5 millimeter around all internal components so that you compensate for distortion, shrinkage, and printer tolerances. So you have a hole in here, give it an extra 0.5 of a millimeter in your design in case it shrinked or it became smaller than expected. Or if it's even distorted, then you can work on it and do post-processing to bring it back to the dimensions you want. For self-tapping holes, then you need to subtract 0.25 of a millimeter from the diameter of the hole if you want the screw or the fastener to bite into the case. Something to keep in mind: instead of extending, you shrink the dimension. You subtract 0.25 of a millimeter from your diameter for that specific hole, so that the thread will, the screw or the fastener will, his thread will eat through that plastic and will keep in place. For port clearances, if you have an electrical port, as we said on the, let's say this is the side view of right hand view of your enclosure, then you have a port, electrical port, or even pneumatic port, whatever it is. Then for all ports or plugs, you need to allow 2 millimeter clearance all over around the port. So if you want to imagine this part, you need to imagine this part as a kind of electrical port, you know. So this part is electrical port. Then in here you need to make sure that this area is 2 millimeters of a clearance, which means 1 millimeter on each side. Adding lugs. Lugs are kind of teeth or support to help in, they're called sometimes cutouts or lips. They will assist with assembly or disassembly and alignment of the different components of the assembly. and in this case for the enclosures. So when you have lugs in here as a male, then you have a female lugs up here. So when you put the two parts together, they will not go only the way they should be, which is the way it aligned them all together. This feature is simple and included in a design, and if you include it in your design, it will increase the strength of your sub-assembled enclosure. It will prevent them from doing any kind of weird movements or shaking. The lugs should be with a minimum of 5 millimeters in width. Ribs and gussets, any kind of supporting material like the one back in here. These are critical design features of injection molding and not very essential for 3D printing. So their inclusion can help reduce and distribute the stress throughout the part and improve rigidity. So ribs and gussets can be designed 75 up to 80% of wall thickness, which we mean the thickness in here. For bosses, you have a hole that needs to be supported all over around. You need to include bosses or supports for the hole in location where the threaded fasteners will be used, so that you will reduce any chance of bulging, distortion, or potential fracture while applying your fastener. Minimum of 1 hole diameter for the wall thickness around the hole is good starting point. But if the hole is for an M5 screw, then you need to include 5 millimeters of wall thickness around the hole. So the hole here for a screw of M5, you need to include 5 millimeter radius around it of thickness. If you're designing the structure of the enclosure, then you want to do uniform wall thicknesses. So the wall thickness all over the enclosure are the same. It's not preferable to have a different wall thicknesses all over the enclosure. I know there's some kind of creative designs that will push you in the corner to make a different wall thicknesses, but make sure to make the wall thicknesses varying. Like you start with 3 millimeters, don't go less than that. You can go 6 millimeters while varying your design in a certain way. You can go to be, so if your enclosure is planned to be like injection molded, like you're doing only proofing for your design, you get your 3D printed part, you like it, eventually you will go with injection molding that part in a certain material, then you need always to have, not a must, but it's highly preferable to have uniform wall thicknesses in your design. Especially if you're using the SLS or SLA technologies. General rules for enclosure designing that we will remember. For enclosures that will have repeated openings and closing, then wear resistance material like SLS nylon should be used. If you are doing rapid prototyping, where your form or fit are being tested, then FDM will provide a fast and low cost method of production. If the enclosure will be subjected to loads, include ribs and bosses to improve the strength of your parts. Then if the enclosure is subjected to loads, as we said, gussets, ribs and bosses are the way to go. Minimum wall thickness should be 2 millimeter, 0.5 millimeter of tolerance around internal components, plus or minus 0.25 millimeters of clearance are good to start with and to consider when designing a 3D printing enclosure.